Hi, everyone. Thank you for joining us today. For our presentation, we have Jaime Vasquez joining us and sharing a little bit about his background and the work that he's done throughout his career. For those of you that are new to these sessions, a little bit about Walter P. Moore is we're an international engineering firm. We have about 26 offices around the world and work on various projects like sports stadiums and arenas, hospitals, airports, schools, universities, and offices. So the portfolio really covers the gamut. As we go through the presentation today, if you have any questions, please type them into the chat box and we will get to them. And with that, I will hand it over to Jaime.
Thank you, Annie. Thank you, and greetings, everyone. Thank you again for joining this presentation. My name is Jaime Vasquez. I'm a structural engineer at Walter P. Moore. I work in the Orlando office where I serve the role of the office operations manager, and I'm also one of the senior project managers. I have been with Walter P. Moore for 27 years, and I have a total of 37 years of experience. So I would like to speak with you for the first few minutes to talk about my journey of how I became a structural engineer. I was born in Central America. I recall my parents telling me that I was a very curious boy, liked to ask lots of questions, and always wanted to know how things worked. And that curiosity always stayed with me and is with me to this day. I recall that around age 10, my uncle, who then was a student, an engineering student, introduced me to the wonders of civil engineering and structural engineering. And it was then at that age that I knew what I wanted to be when I grew up, and that was a structural engineer. But more importantly, I wanted to design buildings. Physics and math has always been of interest to me. My uncle once told me that math is the universal language. With math, one can describe and explain what happens around you. And that statement puzzled me. I was always, like I said before, fascinated with high-rise buildings, especially in New York. So after high school, I moved to New York, where I completed my bachelor's and master's degree, and was very fortunate to work in New York with great mentors whom I credit a great deal for my achievements. I worked there for close to 10 years. And from there, my trek ended in Tampa, where I was fortunate to be hired by Walter P. Moore to work in the Tampa office. And 27 years later, I can still say that these have been the best 27 years of my career. Designing buildings, doing what I love the most. So through the years, I had the fortune and joy of designing several types of buildings. I've designed sports arenas, convention centers. I've designed hospitals and healthcare facilities, parking garages, hotel resorts, and office buildings. And my collaboration on projects spans across the United States, Canada, Central America, Dubai, and Japan. I often tell my children that when I see a project that's been completed, where I collaborated, it gives me a great deal of joy and pride. And I hope that if any of the students that are watching become engineers, architects, or contractors, have the same sensation when they experience their work. This presentation is prepared specifically for the ACE mentorship program. For those of you professionals who are watching this presentation, maybe perhaps a little watered down to you, so please be patient and sit down. For those young, bright students interested in science and engineering, I have tried to keep the topic simple yet interesting, with the intent of sparking the curiosity just enough to consider following this path. The intent of this presentation is to bring awareness that we can solve problems, simple and complex, only if we channel our attention on breaking down these challenges into simple, basic, recognizable steps. I'd like to give first, before we get started, special thanks to the team who helped deliver this incredible project. And I will start with the owner and developer, Lincoln Property, who planned the project, a company that understood the needs in the Orlando market and took a leap to deliver this project that is close to full occupancy now. Also, Hunton Brady Architects, who partnered with Lincoln Property and converted the vision into an exciting design and functional facility. and also challenged the design consultants with this incredible puzzle. Walter P. Moore, of course, who collaborated with the architects and the other consultants to design the building skeleton that helps this icon stand tall and proud across the Orlando skyline. TLC, the mechanical, electrical, plumbing consultants, who in metaphorical terms design the blood vessels and the internal organs that make this building breathe, live, and light up. And of course, last but not least, the Austin Commercial, the contractors, who had the monumental task of taking all of our design solutions that were documented in drawings and computer models and converting them into what you see today in the Orlando skyline. Like I said, this is an exciting project delivered in a tight, constrained environment. The building's property line is only within about 15 feet of an active railroad track. And vibration from the train has always been something of a concern, especially when you build right next to it. So during the early phase of design, our forensic engineering group installed what we call Triaxial Accelerometer. So this is equipment that senses vibration in all three directions, and it was placed within the building footprint. The intent of it was to monitor vibration from the passenger and freight trains for several days. That information was compiled and fed into a data acquisition system that produced plots of those train-induced vibrations. And these plots recorded vibrations parallel to the train tracks, perpendicular to the train tracks, and also in the vertical direction. The plots, when compared against established vibration perception guidelines, indicated that this vibration would not exceed the threshold parameters that have been established as acceptable. Another concern with the proximity to the railroad tracks was keeping the columns, especially the perimeter columns, closest to the track, in a distance away from the train tracks in order to protect them from impact in case there were a train derailment. And there are some guidelines that are provided for designers. And so those perimeter columns on the ground floor were set back approximately 5 feet away in order to clear that derailment threshold. Then at the upper floors from the level 2 and up, the columns were moved back to the building edge. So we end up with ground floor columns that are out of alignment with the columns above, which are a puzzle that we will discuss later in the presentation. So let's talk about the feature project and the topic specifically. Church Street Plaza is a mixed-use facility. This means that it serves different functions. On the ground floor, it has retail space, it has a bank, it has a hotel front desk, cafeteria, and it will also have a future train station. Then levels 2 to 9, it has parking spaces. It has office space from levels 10 to 17. It has a hotel lobby, bar and amenities at level 18, and hotel guest rooms from level 19 through 26. And then at the top, there is mechanical equipment. So let's explore some of the distinct features of these functional spaces. Starting with a parking garage, the floor needs to have wide circulation spaces for the driving aisles, and that is a must. If we were designing just a standalone parking garage, those columns would want to be 60 to 62 feet apart. But because we are mixing different functions, then there are some sacrifices and compromises that need to be made. But in order for this to work, the intent is to keep the columns as far apart as possible. Narrow columns also can help increase the number of available parking spaces. And of course, we need to have sloping ramps to access floors from one level to another. Office spaces, on the other hand, don't work so well with long, narrow columns or columns that are close together. For an office space, you need to have more uniform column spacing. And of course, a hotel floor layout is different from the office space and parking garages. Narrower columns can help improve the guest room layout, and also the spacing for those columns will most likely be different from those of an office space or a parking garage. So it's time for a quick question to summarize what we talked about so far. And while I do that, I would like to ask Annie to see if there are any questions from our viewers. While she checks on the chat, the question is, what particular differences can we find between parking garages, office floors, and hotel floors? We learned before that for each of these spaces that have different functions and have different needs, the efficiency is affected by the column size and their locations. Parking garages, we said before, will generally need to have their inner columns placed farther apart, whereas office spaces can be placed more uniformly.
So we do have a question. So it is, why did you move to Florida, and what are some of the challenges you face when designing buildings in different states?
Okay, very good question. Thank you for that question. The most important reason I moved to Florida, in addition to the weather, moving from New York to Florida, was that I had the opportunity to work for Walter P. Moore. And while I worked in New York, I had not heard much about Walter P. Moore, but a coworker of mine who had been working with Walter P. Moore for several years told me about the greatness of the staff, the mentors, and the type of projects that they were delivering. And so I was inclined to inquire, and I was fortunate to get that opportunity. And can you remind me what the second part of the question is?
What are some of the challenges you face designing buildings in different states?
Yes, thank you. That's another great question. With different states will have different environmental conditions that we need to account for. For instance, in Florida, high-rise buildings may be exposed to high wind pressures, to hurricanes, and things of that nature. Whereas if you go to New York or the northeastern states, it is less likely that you would have the kind of wind pressures that you will see in the Florida and Gulf Coast region. There instead, you will be more concerned about designing for snow loads. Now, if you went across the United States to the West Coast, then the concern would be more about seismic loads, earthquake loads. And so I wouldn't say necessarily each state, but different regions in the United States and across the world would have different challenges that you would have to account for. But the great thing is that the steps in the thinking process that we need to follow is just about the same. We just need to make sure that we understand the loading conditions and that we are able to establish a path for those loads to get down to the foundations where they are intended to be resolved.
Okay. That's the only question for right now. So you can carry on the presentation.
Great, thank you. Okay, so how can we approach the design of this mixed-use facility with efficiency? Is going to be influenced by the column locations and the column sizes. So one important thing would be that instead of focusing on the differences of these parts that are going to be stacked together like a jigsaw puzzle, we should instead look at their similarities and look at what similarities all different buildings with different functions have. So we'll step back for a moment and think about the different buildings that were mentioned before. We talked about sports arenas that are wide open, ample spaces, long span roofs, quite different. And quite different looking than a parking garage where column spacing may be only 60 feet apart, or a hotel resort that would have different intended uses and it would look different, or an office building. So they all have different functions, but they all have to have something in common. So we admit that they are different. Like I said before, they look different, but that's something they have in common is something that we need to start looking for. Let's see if we can find some of those similarities. Let's see what they will have in common, and we'll do what I refer to as peeling of the onion, where we can start taking layers of the building to see if we can find those similarities. And so even though they are unique buildings and serve specific functions, underneath all that architectural cladding, finishes, glass, walls, and all that, these building structures have a lot in common. They all have to perform similar jobs. And what job would that be? I would like to say that they are the backbone or the skeletons of the buildings, the structures that will keep the buildings from collapsing, give them rigidity, and make them stand. Let's think about what else they would have in common. All building structures have to resist lateral loads. Those lateral loads or horizontal loads will be loads from wind, earthquakes, or from other sources. And for that, we rely on what we call lateral load resisting structural elements. These lateral load resisting systems are responsible for providing the building that lateral rigidity. These are rigid elements that have the ability to collect all those horizontal loads and bring them down to the lower floors and eventually to the foundations. These lateral load resisting systems can be shear walls, which are made out of concrete, and you would often see them in buildings around stairs or around elevators. They can also be braced frames or cross bracing, and those are usually made out of steel. Or they can be beam and column moment frames. This could be either steel or concrete. For this project, the lateral load resistance system consists of cast in place concrete shear walls. Let's see what else would these buildings and these structures specifically will have in common, right? Well, all building structures have to support the building self-weight and the occupant loads. And by occupant loads, I refer to the weight of people who would be in the building, office or residential furniture, cars, or anything else that will be stored in the building. And for that, we rely on what we call gravity load framing systems. Examples of this will be columns in the building. It could be beams, which are the horizontal framing elements that span or go between columns, and also the floor slabs. What else could we say that these structures have in common? And this one, for me, and I guess for other structural engineers, is very important. And that is that all buildings and all structures need to have a defined load path. And what do I mean by that? Defining a load path means to identify a continuous path that the loads, whether they are applied externally by wind, earthquake forces, or the loads that are applied internally by the occupants. So it's got to be the path the loads must take to get down to the foundations. And that load path is the roadmap of how you envision all these forces, the wind forces, the earthquake forces, building weight, and all of that, how you envision those loads will travel from where they are applied all the way down to the foundation, which is their final destination. And last but not least, we have to establish a balance between economy and safety. The building has to be functional, that is, it has to serve the intended purpose, but it also has to be safe and it has to be within the building owner's budget. And with that, it's time for another question. And while I do that, I'll ask Annie again to check and see if there are any questions from the viewers. And the question this time is, what do these structures, or what do the structures of these buildings have in common, based on what we talked about before? And I will say that all these structures for the buildings, regardless of the function, are the backbone of the buildings or the skeletons. They all have to resist the lateral loads or horizontal loads. They all have to support the self-weight. That has to be a load path in the structural system, and there has to be a balance between economy and safety.
Okay, we do have a couple more questions. One of which, when I first started at Walter P. Moore, I was very interested in learning about, and that is, what are shear walls?
Yes, I'll explain it here briefly, and then we'll touch on later in the presentation. But in general, shear walls are solid concrete elements, vertical elements that are used in buildings to gather all the horizontal loads that are applied to the building, say wind loads. They have to be collected, right? The wind is applied to the building skin, the exterior walls. The exterior walls will lean against the building floors. The floors will in turn push against something. Something has to prevent them from being unstable. And that something in most cases is shear walls. So shear walls would be the solid elements. Think of them as a tree trunk. You know, if you see a tree in the woods and you see branches that are flapping around, wind blows on those branches, right? And the branches will sway, but they're attached to the trunk. And the trunk will collect all those loads, and from where the branches connect to the trunk, in which case, in our case, is the concrete shear walls, then that load is collected down and it goes down to the roots of the tree. And the roots of the tree are what keep the tree from toppling down. In our case, in the analogy, the foundations will be the roots of our building that will keep it from turning over.
Okay.
I hope that answered the question.
I think it was clear. I've always wondered that myself. You know, people
Okay.
in presentations refer to shear walls, and I'm like, okay.
Yep.
So helpful. Thank you. Okay. Next question is, which layer is designed first? Or do you design each component of the building separately and then puzzle it together?
Just wanted to make sure that I understood the question. I wanted to know if it is referring to specifically for the project, which functional component, whether it was the parking garage or the office building. Is that what the question is?
Yeah. So, you know, what do you design first, and then, or do each of the components of the building get designed separately and then you piece them together?
Yes, a very good question. I'm glad the question was asked. The answer is they all have to be designed together because they will function together. However, there is, I would say, a pre-design, and I'm going to call it a conceptual phase of design, where there will be collaboration between the owner, who has the specific needs for the building, right? The owner wants so many thousands of square feet of office space. He needs to have a hotel that would have several hundred guest rooms, and the building will need to have parking spaces. And so it is, I would say, not a tug of war, but it is a give and take a little bit to trying to find an optimum layout for the building, right? So there are studies that will be done by the architects where they would do an office layout. And with that office layout, then there would be a preliminary study of where the columns would need to be. And then based on those columns would fall, then one would compare, and here is where the structural engineers will come in, would compare and try to define where the columns will need to be in order to support the columns from the second component. And then when that happens, then we have to evaluate if the column location that was discussed will be functional and if it will optimize the parking space layout. So there is give and take until a reasonable column layout and grid layout is defined. And once that is defined, then we look at the building as a whole. We don't look at the independent components, right? We just piece them together. And then as we piece them together, we look at the load path, making sure that the head bone connects to the neck bone and all that, so that it goes down to the foundation. And then we start looking from a general perspective, load is applied, how will the load travel down? So it is looked at as just one component.
Okay, thank you. And that's it for now. So we can continue on with the presentation.
Thank you. So now in our case, we said we have a mixed-use facility, right? And mixed-use facilities have to do the same that we described before, like the other buildings, right? They have to collect lateral loads, downward loads, load path, and all of that. But in this case, there will be some complications, and those complications will be because of the fact that we are stacking building segments that have different functions. And this is sort of getting into what I was discussing earlier, right? We will encounter columns that are not aligned with those of the lower levels, and we will see that each of these segment needs will be different, and they will have different space layout. The same column spacing will not work efficiently for all the needs. And it is true that, at the end of the day, when you look at the building altogether, none of the building segments will have the optimum floor layout. Right? The optimum floor layout is, you will see it only if you have that specific function separated, where you could optimize it without worrying about what will happen to the levels above. So, however, our job as the structural engineers in helping solve this puzzle is to arrange the building structure in a way that provides efficiency with minor compromises and minor transitions. So let's take a closer look at the puzzle so we can find how the pieces of this puzzle will fit together. We have on the screen two sections or two views. Section A, or view A, is a section or a view looking at the long face of the building. The section looking that way. In section B, we're looking at the short side of the building, looking in this direction. So when we look at them, we can see how the spaces transition from, and I don't know if you can see my cursor, maybe not. Can you see my cursor? Yes. So we can see where, where parking levels transition to office levels. There we will see there are columns out of alignment. You can see that in section B on the left side. You can also see how when we go from office spaces to the hotel spaces, the stair walls, in which case we are using as shear walls, are offset, do not align. So we have to deal with this puzzle as well. If you look at section A, you will see how, and it was mentioned earlier, how for a hotel space, the column layout and column needs will be different. So in this case, we have columns that started at the top guest floors, but they stop. And we have to deal with that as well, because extending that column to the office space would not be functional. So these are some of the challenges that structural engineers will need to solve, but we need to find efficient solutions for this puzzle. And for that, we will take a look at one of these challenges. There are so many, but this is just to give you an idea of what the thought process is while designing buildings of this nature. And so to do that, we will look at the transition between building components that have different functions. Let's see how the parking garage transitions to office space. And for that, let's chop off the top floors. And we will also chop off some of the bottom floors. And we will isolate columns that will shift from one position to another. This here is a column that transitions from a parking garage floor to an office floor, right? And I hope you can see there that the columns on the parking garage are shifted closer to the left edge of the building, whereas in the office floor, the column would work best for office space layout if it were shifted to the right, right? So, and that is because parking spaces, as we said before, will benefit from having wider circulation spaces. So the first thing we notice is that with the column misalignment, is that we need to provide some sort of equilibrium. And by equilibrium, I mean prevent anything from moving or shifting, making sure that the loads pushing down are resisted and it's not making the building tumble or pieces go out of alignment, right? So we have the red column that is to the right and the support, well, in between before that. So we have the red column and below it, we have what I will call a transitional column segment, which is a segment that we use so that we can transfer load from the right or red column above to the blue left column on the bottom, right? But when we do that, we notice that there is some misalignment, right? The loads from the column will have a tendency to make that transitional segment rotate, right? If you picture, you can practice this at home, grab a book, put one finger simulating a support on the lower left-hand side and push on the upper right-hand side. You can keep it stable. It is unstable. And so we need to find a way to prevent that rotation. Like if we don't, so there will be rotation unless, and before I proceed with that, we'll take another pause and I'll pick up on the unless shortly. And I wanted to give Annie another chance to see if there are any questions from the viewers while I present this other question. So the question I'm asking here is, why do you think we need to stop column rotation? Well, I believe that we need to restrain the column in order to provide structural stability. We need to restrain that column to restore the equilibrium, and we need to restrain the column to prevent building failure.
Okay, we do have another question.
Yes, Annie.
They look like very slim slabs. Say that 5 times fast.
Yes.
Did that add a lot of complexity to the design process?
Yes, it did add complexity, and it was a conscious decision made, and I will touch on it later in the presentation, but I don't want to leave the question unanswered. The main reason for making the floors thinner, which add a little bit of complexity, but just want to clarify, is complexity that can be addressed efficiently. Right? So making the floors thinner will reduce building height. Okay. So if this were a conventional floor, and I apologize now because I'll be repeating the same when I show the slides, but a conventional floor would have beams and slabs, and we could easily see depths from top of slab to bottom of beam in the order of 21 to 30 inches, depending on whether we use post-tension concrete or not. So if you think about that, whereas if we do the just the floor slab, flat slab, which we could design to be anywhere between 8 to 9 inches. So there's a difference of, say, 20, 21 inches per floor times 26 floors. It's a lot of height. And I'll leave it at that for now because I will explain the benefits of making that decision shortly, but that's an excellent question. And it's a question that we always ask, and a question that we are asked by owners and architects.
Okay.
So great question. I'm glad someone asked that.
Okay, and that is it for right now, so we can continue on.
Thank you, Annie. So we were speaking about the column misalignment. So that misalignment of columns will rotate the transitional segment unless we find a way to provide equilibrium, right? And just going back to the previous question, if we had beams between columns, then we would not be worrying about that rotation, right? The beam itself would have to be designed to support that load, but that would mean that the beam depth would impinge on the clear height that we have on this floor, and we would no longer have the headroom height needed, and that would push the building up. So because of the reasons that I will touch on shortly, in our opinion, the best solution was to deal with the thin floor slabs, because we can find paths to provide that stability, right? And so when we look at the screen, or the image on the screen, we can see that at the point where the upper column meets the transitional segment, there is a floor slab. And concrete is cast monolithically. That means the floor is going to be rigidly attached to both columns. So in order for rotation to happen here, right, as the column wants to move towards the right, it would want to push the floor, but the floor is not letting it do that. When you look at the lower floor as well, the lower floor is rigidly attached to the bottom of that segment and the column on the lower left-hand side. And that rotation is prevented because the floor will not let it happen. And in doing so, then we can provide equilibrium, but we don't stop there. Now we have forces on the floor, and we need to find where and how those forces will go so that we have satisfied that there is equilibrium in the building. I'd like to take just a minute or so and illustrate this equilibrium. If you think of a ladder, right? When we have a ladder, we lean it against the wall. And the ladder is stable because the top portion of the ladder is pushing on the wall. The wall is providing that lateral restraint, is not letting the ladder fall. But if you take away the wall, then there's nothing stopping the ladder, and it would just fall to the ground. So that's what we're seeing in the previous segment that the top floor is doing to the top of the column. In the same manner, at the bottom, we have the floor and we have friction between the bottom of the ladder and the floor that are preventing the ladder from slipping unless we have a wet floor and we have no friction and no stability, and we would have failure. And so the floor and the wall are doing the same job that the top and bottom floors are doing in the previous slide. So the next step then, like I said before, is to see how these restraining forces will travel down to the foundations where they all need to be collected and resolved. And to do that again, we'll take a look at the building and we'll take a slice. Again, we cut off the top, and we will also cut off the bottom, and we will leave two floors in this case. And then we take a closer look at what is happening, not only on the one column, but on the rest of the columns on this side of the building. Right? We talked about each of these columns wanting to rotate, pushing the floors, and the floor doing its job, just preventing that from happening, just being pushed against. And so in order to track where the load is going, we see that this floor is attached to the concrete walls, to the shear walls, which are the stair shafts and the elevator shafts. So the floor itself is leaning on the shear walls. And that is establishing part of the path that this force will need to take. And before we chase the load all the way down, I'll elaborate a little more on the role of shear walls and how they collect the loads and bring them down to the foundation. Right? And you can see on the left side of the screen, again, we have a view of the long side of the building. And there you could appreciate those white long tubular elements, which represent the shear walls. Right? We take advantage of the fact that there need to be stairs going from the bottom to the top, and also that there need to be elevators going. Some of them will go up to maybe just the hotel floor. You can see the short one, and then the rest will go up to the top. So those are good places for us to use as supports, lateral supports for Are Sharewalls. So for that, then what we need in order to collect that load is we need to have those vertical elements that we talked about before that will run the full height of the building. And in our case, as I said before, we will use those concrete shear walls, which will do the job that will collect the load, bring it to the foundation, and provide that much desired lateral stability. Next, I would like to talk about is the building height, and this will touch on the important question that we got from one of our viewers. Right. For the building height, I would like to say that the height has a significant impact on the construction cost. Taller buildings, of course, will need more exterior cladding. And by the cladding, I'm referring to the pretty glass windows and glazing system that surrounds the exterior. So the taller the building, the more surface you have, the more expenses that need to be incurred in order to clad the building. In addition to that, taller buildings will have larger volumes of interior spaces that will need more heating and more cooling in order to maintain controlled temperatures. So that is an additional expense for the larger spaces in taller buildings. And in addition to that, a taller building will need longer columns, longer concrete walls. So there will be additional costs that need to be considered. So now I'm going to elaborate a bit on the question of why, not beams and all that. So we did say that as engineers, we have a choice of recommending what sort of framing to utilize. Right? The key is always selecting and recommending the framing system that works best. In the conventional framing system, we could have used floor and beam slabs with depths of 22 to 30 inches. And for that framing system, if you take an average weight of the floor, it would be something in the order of 130 to 140 pounds per square foot of floor space. Beams, of course, work well because if you're not so familiar with engineering, the rigidity of the building is proportional to the square of the height. So, of course, having deeper floors will prove to have more rigid supporting elements. However, there is what we call post-tension cast-in-place concrete, where you can compensate for that and still make the buildings functional and also economical. So in our case, as mentioned before, we use 8 to 9 inch thick post-tension concrete slabs, and the floor self-weight was in the order of, say, about 100 pounds per square foot. So we have 30 pounds per square foot of floor space difference. The building total square footage is close to 600,000 square feet. So do the math, we're saving 30 pounds times 600,000 square feet. So that would be additional weight that the columns will need to support, and additional weight the foundations will need to support. Right. So by using the thinner floor slab framing, the floor height, not the floor height, but the building height can be reduced on average, say 20 to 21 inches per floor. And we have 26 elevated floors. So if we do the math, 26 times 21, that will be close to about 45 feet. So we are going to be shortening the building height by 45 feet, right? And we could say that compared to a conventional cast-in-place floor slab and beam system that would have been 40 feet taller, when using the thinner slab, there is approximately a 14% reduction of exterior building skin. Exterior cladding can vary from $50 to sometimes even $80 to $90 per square foot. So there are substantial savings there that can prove to be more efficient than having a taller building. In addition to that, the shorter building will see a reduction of volume of space to be conditioned of roughly about 9%. So that would save on heating and cooling and electricity as well. And in addition to that, there will roughly be a 23% reduction of the building slab self-weight, which in turn will reduce the foundation loads. And this reduction in building height also reduces the height of the building that will be exposed to wind. Lateral loads on foundations increase exponentially. That is, the taller the building, of course, there is more wind, but the impact is proportional to the square of the building height. And so in our case, for this building, the reduction in building height resulted in a reduction of roughly about 27% of the wind effect on the shear wall foundations. So it's worth mentioning also that less concrete will also mean less carbon footprint. And I think we had a presentation that talked about that in the past. And so with this, I leave the floor open with questions to see if there are any more questions from the viewers.
All right, great presentation. Thank you, Jaime. Does anybody else have any other questions? Type them into the chat. Give everybody a couple more minutes.
Sure.
It doesn't look like anyone's typing, so
Great.
I think we are probably good for today.
Great. Well, thank you again for tuning in and listening to the presentation. Thank you, Annie.
Thank you, everybody, for joining, and we will see you next time.
Awesome. Thank you again, and have a good night.